So good morning all. So I'll be talking about the ocean color application. It is specific to Indian Ocean region. Uh, so I just made a small add-on to this one. I just added an operational to that. See, Indian National Center for Ocean Information Services. Our mandate is to provide the ocean information and advisory services to various stakeholders for operational, mainly for operational reason and to for various stakeholders. Uh, and we actually bridge between the science and the society. So mostly it goes for the societal applications. So there are several products and services which we give using ocean satellite data and also the models. But I'll be focusing mostly on the ocean color data. So before I start, just just to set up the pace, when we see these nice images of ocean color remote sensing data, there's a lot going on to that. It's not like simply the satellite will give you these images. So you must have learned from last 1 week the interaction of the light with the matter, the absorption, scattering, and so on. So after all that uh, data acquisition by the satellite, doing all these corrections, and finally getting those reflectance, and then you get an usable geophysical products from the ocean color data, which can be used further for the application. So I'll be talking from level 2 onwards. So I'm not going to talk about level 0, level 1 data, level 2 and level 3, which can be used for the operational applications. So just to start with, just a quick image of, you see this great wall of Somalia coast. Hope my pointer is visible here. Yeah. So these are high chlorophyll band, which high chlorophyll, which is at the periphery of these currents, Somalian currents, so which is mostly caused by the northeasterly direction of the Somalian currents. And what you see here is an mission composite image of chlorophyll A, that is from Modis Aqua, and a lot of things can be identified from here, lot of features. So this images actually comes after doing radiometric corrections and applying a suitable algorithms and so on. So I'll be talking only from level 2 to level 3 perspectives. Before I start, a small disclaimer. Maybe you know the advantages of remote sensing. You can get the data from an inaccessible areas. You have a global coverage. You can also study the teleconnections using the remote sensing data. But just to keep in your mind that remote sensing is an indirect measurements. It will not give you directly the geophysical products what we get. So we need to understand the different signals or the processes or factors which has an impact on the signals. We also have to consider the degradation of the instrument from time to time and the assumptions which have been made in various models and algorithms to derive the geophysical products. And one of the most important thing before using the ocean color data for the applications is the validation. The data has to be validated. So now there are many agencies who does this for us. So, but if you are going for a very regional specific studies, then it's always better to know the accuracy and the error which is there in the data. So just a quick illustration which I came across when I was intensively working on the Moody's data. So if you look at the image on the left side and the right side, so the left side image is the Moody's Aqua chlorophyll on 10th Feb uh, at 1 kilometer resolution. This what's something which we got from the satellite. And what you see on the right side is the image, the same day's data at 4 kilometer resolution. So it's a bin to 4 kilometer right side and one. So you see a lot of artifacts at the edge of that one. But if you want to use this data for, let's say, identifying a smooth features, and that too with some kind of an automatic process, so there is a possibility that you may get some error into that. because this is not a smooth feature. There is a gap in between that. So when we try to understand why it is so, we posted in the forum, and what we got is that, so when a satellite detects or satellite looks at a particular pixel, or if you, which is the smallest area which can be detectable, and the spatial resolution which is defined by the height of the sensor and its instantaneous field of view at what angle actually it's looking at it. So at nadir, the the resolution or the pixel size is relatively a little smaller as compared to when it goes at the edge of the swath. So if you have a sensor with a swath of, let's say, 1400 kilometers, so when it looks at the center, pixel size will be slightly less as compared to when it goes to the edge of the swath. So in that, because of that, when you bin it, because when you bin it or grid it to a square, so a small gap remains into that. So that may create an artifact at the edge of the swath. So these are the also important things which need to be considered when use that data for your application. Like if you're going for a larger scale, maybe 4 kilometer is good enough. Maybe if you want to do at the coastal or very small scale, you need to go for 1 kilometer. So the message is that you need to use the data wisely to use it for an operational application. Now, coming to ocean color remote sensing, there are a lot of things which can be done with ocean color remote sensing. I have just projected few of those. And considering the time constraint, I'm going to focus on only the operational applications. So you can use the data to understand the global carbon cycle, because the phytoplankton, which is there in the ocean, are the primary producers and has a capability to take up the carbon dioxide and give up the oxygen. And if you can estimate the rate of the uptake, so you can always estimate like what are the carbon fluxes into it. Primary productivity, of course, and the food web, because it is also depending on the phytoplankton. To a large light, we can estimate always what is available of the light, and it is also available through remote sensing. Uh, Marine fishery advisory services, which is the next step to a productivity, which is also an operational service which INCOIS is giving to all fishermen on daily basis. In addition to that, there are also applications like risk mapping, like we can identify the blooms. I'll be talking a little bit more detail on that, eutrophication, pollution, a marine heat wave, which is also become a very important parameter as far as the various ecosystems are concerned, especially the coral reefs and all. So where we can use it, we can also use it to give various water quality services, because there are many parameters which can derive from the satellite remote sensing. And one more important thing is we can bridge the physics with the biology using the ocean color remote sensing data, or the products which we generate from the remote sensing. So I'll be mostly focusing on the biophysical processes, risk mapping, and marine fishery advisory services. So, so what actually satellite gives? So satellite will not come and tell you, okay, this is the chlorophyll, or this is the organic matter, or this is a suspended sediment. So what it will give you is, it will give you some information or some digital numbers in various bands. And then based on the different combination of the bands or the features which are available, we need to derive the geophysical parameters and then subsequently use this for the operational application. And for that, we need to have an understanding of the ecosystem processes. Like this is one illustration, what you can see here. The data, the remote sensing reflectance from the HyperPro in two different water types. And the top one is very near to the coast, and the down one is in the open ocean. And this is the spectral signature. So if you look at the maximum energy in the bottom waters, it is mostly in the blue, and the top one is to the green and greenish yellow. So this is what will be given by the satellite, only the your remote sensing reflectors. Now, why it is varying or why it is changing, that has to be done based on the understanding of the ecosystem or the ecosystem parameters. Like for example, in this case, if you see the concentration of CDOM, it's like same in both the cases. The total suspended matter is also within the same range. And the chlorophyll concentration, if you see, it's almost like 20 times more in the green water as compared to blue water. So we can always say, like, because of the high chlorophyll concentration, the spectral remote sensing, the peak energy in the spectral remote sensing is moving towards the longer wavelength, and it gives us the impression of green to yellow color. So all this understanding goes in designing the various bands in the satellite ocean color remote sensing. David has already spoken about it. I'll not go more detail into that, but this is an example of Ocean Set 3 Ocean Color Monitor, which is very recently launched by Indian Space Research Organization. And the bands are chosen based on the different applications. So it is almost similar to that of CViews and MODIS. In addition to that, there is one band which is at 566, which is dedicated to for phycocyanin absorption, which is an indicator of a trichodesmium bloom. So the proposal was given based on the recurring bloom of trichodesmium, which occurs along the southwest coast of India. And based on the in situ studies, what was found that it is sensitive to 566 nanometer band. So accordingly, that band is added. And the rest all bands have a different application, like the blue and green used for mostly for estimation of the chlorophyll, and then also for the CDOM, shorter wavelength, and then longer wavelength for the atmospheric correction, which is in the near infrared. So all the bands are selected based on the application, and which have been actually decided based on your in situ data. So now coming to INCOIS. So we have a dedicated ground station which acquires Modis Aqua and also the NPP, that is weeds. And in addition to that, we also get the data from Sentinel and Ocean Set 3. So that also is also added to our ground station. So this comes at a real time to INCOIS. And then there is a processing chain which will process this from level 1B to level 2 and level 3 data, which is a graded product. And that product is used for different applications. The first thing, different applications. So let's go to the, before I go to the actual services, I just want to, for a few applications of the ocean color remote sensing data in general. So what you see here are the monthly composite of chlorophyll uh, from Modis Aqua. And the peculiar thing to see in the Arabian Sea, this is the North Arabian Sea, there's the Northern Indian Ocean. During the monsoon time, that is the southwest monsoon, June, July, August, you see a very high chlorophyll patch along the southeastern coast of the Arabian Sea and also of Somalia, and which subsides during the intermonsoon time. Again, in the winter time, that is December, January, there's a high patch of chlorophyll in the northern Arabian Sea. So just to understand why, what are the things, because the ocean biological processes are mostly derived by the physical processes, of course, through chemistry. So in North Indian Ocean, there's a very typical feature, what we call it as a monsoon. Monsoon is a seasonal reversal of the wind pattern. So during the southwest monsoon, that is roughly June, July, August, the wind is mainly from the ocean side, that is the southwest side. So during the southwest side, and the currents along the western Indian Ocean goes towards north, and along the eastern Arabian Sea, or the eastern coast of the Arabian Sea, it goes down. So because of that, there is an upwelling, intense upwelling occurs along the Somalia coast and also along the southeastern Arabian Sea. So due to that, we can see that high chlorophyll patch into this. Now, what happens during the winter is that there's a reversal of the wind. Mostly starts roughly from the end of December to January, and it peaks sometimes February, March. So this wind is coming from the northeast, which is from the land. So this wind is relatively dry, and because of that, the evaporation is more as compared to southwest monsoon. So because of that, your surface layer becomes more dense and it starts sinking. They call it as a winter mixing. So it starts sinking and then it is compensated by the bottom waters, which is rich in nutrients, and that triggers the bloom in the northern Arabian Sea. So that is also very peculiar. For this is even seen in the CZCS images also. So it's not, it's a recurring bloom which occurs, means it has been occurring, but uh, the remote sensing has been also used to study what is the intensity of that particular bloom. So what has happened now in recent days is that there is a phase shift in the uh, organisms which blooms. So initially it used to be an diatom, which is known to be like a good for the ecosystem, but now it has been changing to a noctiluca. So there's a phase shift in the organisms which blooms, but there is a bloom, but there's a phase shift. Now, why we are really worrying about the noctiluca? Because it is a heterotroph. It can feed on the phytoplankton itself. So if the noctiluca bloom, if it increases, then there may be a threat to the ecosystem. So remote sensing data has really given us understanding on this particular phenomena. Now coming to the next application, which related to biophysical processes, is the penetrative radiant flux. So we have been talking about the chlorophyll a lot, but there is also one more parameter which can be derived from the satellite is downwelling diffuse attenuation coefficient. We call it as a KD. So KD actually is like an how your light penetrating towards within the water column, what is the diffusion of that particular light. So the light will always decrease exponentially with depth, irrespective of your water column and irrespective of your water constituents. But of the uh, the slope here will depend on the turbidity. So if your water is more turbid, then your slope will be more. And if your water is clear, then the slope will be less. So your KD, if KD is high, that means the water is more turbid. And your KD is low, that means your water is less turbid. And from this KD, we can also estimate, like we know the light at the surface. And if we know the diffuse attenuation coefficient, then we can always calculate the light at a different level using the Beard-Lambert's law. So based on that, if you look at this slide, what you see on top is an equation which gives the SST tendency. So it is used in the mixed layer modeling. So in the mixed layer model, this equation is used to estimate the SST tendency. So there was an experiment done in Bay of Bengal where it was found that the sea surface temperature was overestimated by the model. So why it is so? Because the model assumes that all the light which comes, there's a major source of energy, it is trapped within the mixed layer. So 100% of the light is there within the mixed layer. So that was the assumption. Because of that, SST was overestimated. When the in situ experiment was done, so what was found is that almost 30% of the light, because the Bay of Bengal, the mixed layer is very shallow. In northern, it may be like 15 to 20 meters. As you come south, it may be like 30, 35 meters, not more than that, because of the rivers getting the fresh water from the Ganges. So what was found is that 30% of the light goes below the mixed layer. So the assumption of 100% light within the mixer is not true. And when the actual values were substituted in the model based on the in situ radiometric measurements, what was found is that there was an improvement in the estimation of the sea surface temperature. So remote sensing can be also used to understand these physical processes uh, from the data what is available. Okay, I'll skip this. Okay, so that's all about a very general understanding how we can use the remote sensing in different applications. Now coming to the services, the first one what I'm talking about is the potential fishing zone advisory services. So that means, so if you look at the food chain, so mainly in oceanic food chain, it starts from the primary productivity, which is mainly by the phytoplankton. So we have a primary product producers, then we have a primary consumers, which are like a zooplanktons, and then we have secondary consumers, maybe small fish, then goes a higher order like bigger fish and bigger. That is a typical food chain in the ocean. Now, we can estimate the primary productivity from the satellite using the chlorophyll. It's again, it's not a direct estimation, it's indirect estimation. From there, we can link between the phytoplankton, then zooplankton, phytoplankton, primary productivity, chlorophyll, primary productivity, phytoplankton, then zooplankton, and then fishes. So we can model this thing based on the source data from the satellite. But again, apart from the chlorophyll, because the productivity, if you see the frontal zone in the ocean, the fronts are mainly the region where there are two water masses actually meet. So those frontal zones are normally very productive because the fronts are created once if because of the vertical advection or maybe because of the convective mixing. So both the ways you get the fronts. So in either case, the subsurface water, which is rich in nutrients and also in oxygen, which comes to the surface, and normally the productivity at these frontal zones are very high. So what we do is that first we map the frontal zone using the sea surface temperature, because at frontal zone can be very well identified using the sea surface temperature. There's a very steep gradient. So first we identify the frontal zone using the sea surface temperature, and then we use the chlorophyll to see whether those areas are productive or not. And using all both these parameters, so the areas which high chlorophyll associated with the frontal zone are mapped as a potential fishing zone. So there are some intermediate steps in between, which I'm not going in detail. And based on that, the features such as the eddies or rings or some meandering patterns and all those things have been identified. And those areas have been marked as a zone which are having more potential of fisheries. And we give this product to the fishermen. Uh, they use that, and along with that information, we also give, like we have a fish landing centers from where all these fishing boats and trawlers operate. So we also provide them the distance for this frontal zone from those landing centers. So I'll show you maybe after this on our website how the data is being disseminated. Now, next one is the coral bleaching alert. So coral bleaching alert mainly started with the sea surface temperature data, because we have areas with very active and live corals. So on the west coast, also on the east coast, and in the Andaman and Nicobar region. So this coral bleaching alert primarily uses the sea surface temperature data, and it calculates the anomaly. First, it creates a climatology of the sea surface temperature, and then the anomaly, and then based on that, the degree of heating is calculated, and based on the in situ experiments, there are some thresholds are given, and if the anomaly goes beyond that threshold, so it is been marked as warning, like no stress or watch or warning. So there are three categories. and this is calculated every bi-weekly. Now, in addition to that, the new for coral bleaching, we also included the downwelling diffuse attenuation coefficients also into that, because the turbidity is also one more factor which may have impact on the corals. Apart from that, the marine heat wave. So marine heat wave is like a discrete or prolonged anomaly of the warm water event, which persists for more than 2 days, about 90 percentile of climatology. So that is the definition of the marine heat waves. So these marine heat waves are also generated using the sea surface temperature, daily sea surface temperature. We take it from the different satellites and we calculate and we provide it on a daily basis. And we also do the assessment of this marine heat wave on the corals. So if you look at this plot here, which gives the percentage of the coral bleaching, which is been determined in situ, and the intensity of the marine heat waves, there is a strong positive correlation between these two. And this is an example of this is an eastern Indian Ocean, that is of Andaman and Nicobar, where the left panel you see the intensity of the marine heat waves, and right side is the percentage of coral bleaching. So wherever there is a high intensity of heat wave, there is a high possibility of there is a bleaching event happened along the eastern side of the Andaman Island. So this heat wave is also given along with the coral bleaching. So we can map this risk using the ocean color, the sea surface temperature from the satellite data. Next is one more service what we give using the ocean color data is the algal bloom information service. So for algal bloom information service, we use various parameters, primarily chlorophyll A concentration, sea surface temperature. We also use the anomaly, and there are other parameters like the algal bloom index and also the phytoplankton size classes. So I'll go a little bit more detail into this, the parameters or the way approach what we have used to determine the algal bloom information service. So, and okay, in addition to that, we also give a spread of Noctiluca and diatom along with that, which is also estimated using the remote sensing reflectance data. So why we are really bothered about this algal bloom information service is because what we have found is the occurrences of the dinoflagellates, primarily the Noctiluca, is been increasing along the Indian coast for last within this is decade. And the worry is that if it is a normal food chain in the water, which goes like physical processes, the nutrient flux and phytoplankton composition, those zooplankton, small fish, large fish, it's fine. That's something which should actually occur. But if there is a Noctiluca, it is a heterotroph and it itself feeds on the phytoplankton. So there's a possibility like the food chain itself may get disturbed and the fisheries may get declined. So that's why we started monitoring this algal blooms. In addition to that, whenever there is a bloom of the large phytoplanktons or the dinoflagellate, there is an more export after the degradation. So the export flux after degradation also increases, which can also tends to increase or expand the oxygen minimum zone, which is a very which is prevalent in the Arabian Sea. You can see just below the 1,000 meters, there is a thick oxygen minimum zone. And if there is an mixing is more intensive, it's possible that those hypoxic water can also come to the surface. So that's why we are monitoring this algal blooms and also the oxygen minimum zone on regular basis. So just a few slides on what is our approach to monitor this algal bloom, which has been given as a service. So we did an extensive studies on using the remote sensing data on how the various parameter varies when there is a bloom or when there is a no bloom. So if you look at this is a chlorophyll. So during the active phase of the bloom, the chlorophyll concentration from the satellite goes like more than 10 milligram per meter cube, where the typical concentration may be lying between 1 milligram per meter cube, but it goes up to 10 during that bloom phase. And then the algal bloom index, which has been computed using the published algorithm. So the algal bloom chlorophyll. So this is a specific product which is available, which is chlorophyll algal bloom index, which says that it removes that anomaly in high. Sometimes there may be some spike in the satellite data, so it removes that spike and then normalizes the concentration, but that also goes very high during the bloom period. Coming to sea surface temperature, because that's the period when we experience the intense algal bloom, is mostly during the winter time when the sea surface temperature is roughly 24 degrees. So normally it is like 30 degrees, but it goes up less than, sometimes little less than the 24 degrees. So that is a one indicator. So most of the bloom what we occur and what we see is associated with low sea surface temperature of roughly 24 degrees. And there is one more product which we are deriving from satellite is the bloom index. So bloom index is, this is the equation what you can see. It uses the 510 and 555 nanometer and 443 nanometer bands. And based on the spectral signal, we calculate the bloom index. And this bloom index is normally positive during the active phase of the bloom, and it is negative during the decay phase of the. Yes. This is modest what I'm showing. So based on that is also a one more indicator. In addition to that, when we looked at the chlorophyll anomaly uh, with it's like a 30 days of rolling chlorophyll anomaly. And if we can take the lag of 1 day, and if you take the lag of 5 days, so when we take the lag of 5 days with the rolling chlorophyll anomaly, we can also detect the high chlorophyll signal 1 day before it is going to actually peak. It's based on the exercise what we did using the remote sensing data. So that is also one indicator, because that bloom actually, when it starts peaking, we get the signal in the anomaly itself. And then there are some more product, like one more product what we use is the phytoplankton size classes. So that is also available. It can derive from the ocean color remote sensing data. It can give you in picoplankton, nanoplankton, and microplankton. The idea behind using this product is that usually when there is dinoflagellate, the size of the dinoflagellate is much larger as compared to that of the diatom. So if you have a larger phytoplankton, that is one indicator that there is a possibility it can be a dinoflagellate. So that is one indicator using the microplankton. And there's one study carried out by Dwivedi et al. 2015, which we used to discriminate between the noctiluca and the diatom, which is again based on the spectral remote sensing. So you see this plot on the top left. We have three spectral remote sensing reflectances, uh, where the blue one, the top one, is taken in the waters which was there was no bloom, or the clear waters. The red one was in the waters which was dominated by the diatom, and the pink one is the spectral remote sensing reflectance in the waters which was dominated by Noctiluca scintillans in northern Arabian Sea. So the slope of the remote sensing reflectance between 450 to 550 nanometer is positive in case of the Noctiluca and negative in case of the diatom. So both are in different phase. So using that criteria, uh, we can differentiate between the Noctiluca and the diatom. So that also has been taken as one of the parameters. So using both of this combination, we give a map with the information on the occurrence of bloom. So whether there is a bloom or it is a non-bloom, and what are the types of the plankton which are available, like whether it is Noctiluca or which are diatoms. So it is only right now we give the spread of that. There is no absolute magnitude or the number for that, but it is only the spread, the area of this thing. So this is also available on our website. So this is taken from the 7th of November, where you can see there is a bloom of northern of Pakistan, and there is also on the southwestern Bay of Bengal. Okay, I think so. We have also done the validation of this particular product, which is also available on our website. There was a massive bloom of Noctiluca of Kerala in 2021, and we used the same product to evaluate it. And this is what it looks like. So this is really increasing along the Indian coast. So that's why we are continuously monitoring this one. And we are also giving this information along with the potential fishing zone advisory services, because usually what happens when there is a high chlorophyll, we mark that region as a potential for the fisheries, but it may not be the case if it is if the Noctiluca bloom is prevailing on the same area. So that information also goes along with it. Yeah, so I think that's all I have.